Key principles for estimating emissions. 1. Collaboration. The process engineer knows the process, the modeler knows the model. Collaboration between the two is essential for accurate emissions estimation. Establish an open relationship where questions are encouraged and expertise is shared. Avoid pretension and ask tough questions to ensure realistic and representative estimates. 2. Non-blame environment. Focus on estimating emissions accurately rather than assigning blame for errors. Create an environment of trust where team members can seek help without fear of criticism. Establish practical, reproducible procedures for estimating emissions, not for chasing down errors to ostracize those responsible. 3. Iterative process. Accept that iterations to improve the model's accuracy are unavoidable due to varying professional opinions, potential errors, and changes in procedures. Allocate resources for iterations and clarify in the project scope the limit on the number of iterations. Recognize the complexity of quantifying emissions from dynamic processes and prepare for necessary changes. 4. Separation of roles. Assign emissions inventory and permitting tasks to separate individuals to ensure thoroughness and accuracy. Each person should be competent in their area and work well in collaboration. 5. Documentation. Maintain detailed paper and electronic trails to ensure reproducibility of the emissions estimate. Ask whether the steps can be reproduced after a few months using the documentation provided. Avoid carelessness that could result in lost or poorly documented estimates, which may need to be recreated. Latest approaches in emissions estimation. 6. Advanced modeling software. Utilize the latest software tools designed for emissions estimation, such as Emission Master, which conform to EPA-approved methodologies. Software tools can simulate various emission activities, including charge or vessel filling, depressurization, purge sweep, heating, and storage tank operations. 7. Data integration and real-time monitoring. Integrate emissions estimation software with real-time data monitoring systems for continuous updates and validation of emissions data. Use IoT devices and sensors to collect data on process conditions and emissions in real time, enhancing the accuracy and timeliness of estimates. 8. Machine learning and AI. Leverage machine learning algorithms and artificial intelligence to analyze historical emissions data and predict future emissions trends. AI can help identify patterns and anomalies in emissions data, providing insights for process optimization and emissions reduction. 9. Sustainability and compliance. Ensure emissions estimates align with sustainability goals and regulatory compliance requirements. Incorporate best practices for reducing emissions, such as implementing cleaner technologies and optimizing process efficiencies. 10. Stakeholder engagement. Engage stakeholders, including regulatory bodies, community representatives, and environmental groups, in the emissions estimation process. Transparent communication and collaboration with stakeholders can enhance trust and ensure that emissions estimates are aligned with community and environmental expectations. By incorporating these latest approaches, emissions estimation becomes more accurate, reliable, and aligned with modern technological advancements and sustainability practices. Emission estimation methods. 1. Charge or vessel filling. When liquid is pumped from one vessel to another, emissions are measured based on the volume of headspace vapors displaced in the receiving vessel by the incoming liquid. The receiving tank may vary in fullness. For a conservative estimate, use the highest temperature or concentration of the compound from either the sending or receiving vessel. 2. Depressurization. Emissions occur when the pressure in a vessel is reduced isothermally, releasing volatile components from the headspace. The model assumes non-condensables leaving the vessel are saturated with headspace volatiles, with vapor pressures calculated using the midpoint pressure between initial and final pressures. 3. Purge, sweep. Non-condensable gas is used in liquid storage vessels to prevent explosive atmospheres or move liquids. This gas is usually saturated with the liquid's volatile components. Emission rates are provided based on Raoult's law, considering the purge or sweep rate. 4. Heating. This method accounts for thermal expansion of the vessel gas space and the increase in vapor pressure of the stored liquid during heating. Emissions are estimated using thermal displacement and average vapor concentrations at initial and final temperatures. 5. Storage tank. Calculates both breathing losses and total volumetric displacement working losses from simple inputs like tank dimensions, vent relief settings, annual turnovers, and local meteorology. Latest approaches in emission estimation methods. 6. Vacuum operations. Simulate emissions from operations conducted under vacuum, considering the gas evolution and potential emissions from the process. 7. Gas evolution. Model emissions from gas evolution in processes where gases are released due to chemical reactions or changes in temperature and pressure. 8. Solids drying. Estimate emissions from the drying of solids, taking into account the volatile organic compounds, VOCs, released during the drying process. 9. Empty vessel purges. Simulate emissions from purging empty vessels with inert gases to remove residual volatile compounds before refilling or maintenance. 10. Process condensers and after condensers. Incorporate process condensers and after condensers in the modeling software to capture and condense emissions before they are released into the atmosphere. These devices help to more accurately estimate emissions by accounting for condensable fractions of the emissions. 11. Scrubbers and control devices. Use emissions estimation programs to simulate the effect of scrubbers and other control devices on reducing emissions. This includes accounting for the efficiency of these devices in removing pollutants from the emission stream. 12. Integration with real-time data. Enhance emission estimates by integrating modeling software with real-time data from IoT sensors and monitoring systems. Real-time data provides continuous updates and validation, proving the accuracy of emission estimates. 13. Use of AI and machine learning. Apply AI and machine learning to analyze historical emissions data, predict future emissions, and optimize process parameters to minimize emissions. These technologies can identify patterns and provide actionable insights for emission reduction. 14. Scenario analysis and sensitivity testing. Perform scenario analysis and sensitivity testing to understand the impact of different operational conditions on emissions. This helps in identifying critical parameters that significantly influence emissions and allows for targeted interventions. By leveraging these advanced methods and approaches, emission estimation becomes more precise, comprehensive, and aligned with the latest technological advancements, ensuring better environmental compliance and sustainability. Advanced emissions estimation. 1. Vacuum operations. Simulate emissions from operations conducted under vacuum, considering the gas evolution and potential emissions from the process. 2. Gas evolution. Model emissions from gas evolution in processes where gases are released due to chemical reactions or changes in temperature and pressure. 3. Solids drying. Estimate emissions from the drying of solids, taking into account the volatile organic compounds, VOCs, released during the drying process. 4. Empty vessel purges. Simulate emissions from purging empty vessels with inert gases to remove residual volatile compounds before refilling or maintenance. Latest approaches in advanced emissions estimation. 5. Process condensers and after condensers. Incorporate process condensers and after condensers in the modeling software to capture and condense emissions before they are released into the atmosphere. These devices help to more accurately estimate emissions by accounting for condensable fractions of the emissions. 6. Scrubbers and control devices. Use emissions estimation programs to simulate the effect of scrubbers and other control devices on reducing emissions. This includes accounting for the efficiency of these devices in removing pollutants from the emission stream. 7. Integration with real-time data. Enhance emission estimates by integrating modeling software with real-time data from IoT sensors and monitoring systems. Real-time data provides continuous updates and validation, improving the accuracy of emission estimates. 8. Use of AI and machine learning. Apply AI and machine learning to analyze historical emissions data, predict future emissions, and optimize process parameters to minimize emissions. These technologies can identify patterns and provide actionable insights for emission reduction. 9. Scenario analysis and sensitivity testing. Perform scenario analysis and sensitivity testing to understand the impact of different operational conditions on emissions. This helps in identifying critical parameters that significantly influence emissions and allows for targeted interventions. 10. Life cycle emissions assessment. Consider the entire life cycle of processes and equipment when estimating emissions, from raw material extraction to end-of-life disposal. Life cycle assessment provides a comprehensive view of the emissions associated with each stage of a process or product, enabling more informed decision-making. 11. Environmental impact modeling. Use advanced modeling techniques to predict the environmental impact of emissions on air quality, human health, and ecosystems. These models can simulate the dispersion, transformation, and deposition of pollutants, providing a holistic view of the emissions effects. 12. Regulatory compliance and reporting. Ensure that emissions estimate regulatory requirements and are aligned with reporting standards. Use software tools that facilitate compliance with local, national, and international regulations, simplifying the reporting process. 13. Stakeholder engagement and transparency. Engage stakeholders, including regulatory bodies, community representatives, and environmental groups in the emissions estimation process. Transparent communication and collaboration with stakeholders can enhance trust and ensure that emissions estimates are aligned with community and environmental expectations. 14. Sustainability metrics and targets. Integrate sustainability metrics and targets into the emissions estimation process. Use these metrics to track progress toward emissions reduction goals and to identify opportunities for further improvements. By adopting these latest approaches, advanced emissions estimation becomes more precise, comprehensive, and aligned with modern technological advancements and sustainability practices.